Yeah. Okay. Well, thank you to Talia and GlobalSaké for the invitation. I'm very happy to be here. Happy to be with everybody. And yeah, so this is what I do for a living. I teach machine learning and artificial intelligence. So I really enjoy. I enjoy teaching as much as I enjoy learning, and so I learn from everybody. And I'm gonna start. Actually, my title was something like storytelling through data, friendly introduction. I make my titles very long just in case I change something, and then I make sure I hit something on the title. So the more accurate thing is the sentence in the middle, a friendly introduction to either machine learning or deep learning, right? So I'll start with a question, and I like to ask this question to everybody because I get a great answer from most people, including if you've never heard the term. Everybody has an idea of what machine learning is, right? So what is machine learning to you? I would like to hear from somebody.
Parameter optimization.
Parameter optimization, yes, that's very good. Definitely you have some parameters and you want to find the best possible parameters. Any more like, more pedestrian answer, more, how do you explain it to a, yes?
It's an area of computer science that deals with how to get machines to generalize data onto new sets of data and essentially learn the way humans learn.
Exactly. Cool, we have an audience of experts. It's going to be harder. So it is an area of machine learning where you're looking to teach the computer something and make the computer just guess, like generalize on future data, right? Anybody who doesn't know a technical definition wants to tell me something what they think machine learning is?
Teach machine to learn.
Teach machines to learn. Perfect. That's yeah. The way I see it is you're teaching a computer to think like a human. So humans like remember things and try to generalize from previous situations, or you kind of maybe you'll get a little better in how you do things. So it's basically that, like teaching. The way I see it is teaching computers to think like humans. And so let me give you another question. What is it good for? Like, what is your favorite application of machine learning? Anybody?
Here's
Yes.
basic for diagnostics.
For diagnostics, it's fantastic. Yeah, that's one of my favorite applications too. For medical diagnosis, it's actually beating doctors at many things already. There was recently a paper of Sebastian Thur and other people at Stanford where they take pictures of moles and they can tell if it's the computer can tell if it's cancerous or not with 70% accuracy, and the best board certified dermatologists have 60% accuracy. So that kind of stuff is very useful. Any other applications?
Translation.
Say that again?
Translation.
Translation is fantastic. It's one of the really fascinating ones. Soon probably they'll have a chip and maybe you can speak in one language and the person understands another one. So here are my favorite applications. One, as you mentioned, and we didn't plan this, but actually we're going to say a lot of things you said. Playing Go, like with DeepMind, machines beat humans at playing Go much harder than chess. Actually, the number of states in a Go board is more than the number of atoms in the universe. And it was fascinating. I didn't think it was going to happen that soon, that a computer can beat humans at Go. But it not only beat the best human at Go, but the new computer already beat this one very badly. So this is going really fast. Another one is a little older, but it's still pretty fascinating, beating humans at Jeopardy. So this is a lot of applications of natural language processing, and pretty badly. Look at that, 77,000 versus like 20,000. So pretty fascinating applications. Another one that's very trendy, obviously, in Silicon Valley, the self-driving car. Cars soon are going to just drive themselves everywhere, all with the use of machine learning. So how I see machine learning is like a fortune teller, right? As you said, it generalizes on data. So it'll tell you things. It'll learn from previous stuff and will tell you like a prediction. This is what I think will happen. So there's two types of predictive machine learning. There's two types. The fortune teller can tell you things like yes or no to your answers, and that's called classification. Or the computer can tell you a number like 5 or 7 or 4.3 or minus pi or something, and that's called regression. Okay, so these are the two main forms of predictive machine learning, and let me give you some more applications that I like. In classification, some of my favorite applications are spam detection. So the computer can tell you your email is spam or not spam. That's yes or no. Face detection, it can tell you if in the image there is a certain face or not. Things like stock, for example. This can tell you, you should buy stock or should not buy stock. As you said, the medical application. It can tell you, based on your symptoms, you're sick or you're healthy. And even the self-driving car can be taken as a classification problem. So you can do things like tell it to turn right or not turn right, or brake or not brake, etc. What about regression? Can anybody think of regression examples?
And where the faces?
Say that again.
Where the faces in the image?
Fabrication. Yeah, that can be taken as regression or classification. Let's go for simple ones. Things like housing prices. That's the first example everybody sees in regression, right? You want to predict how much is the house going to cost. That's not a yes or no, that's a value. Things like the spread of a virus. If it's a big number, then the virus will spread, and if it's a small number, then it's contained. Or even stock market, right? You can predict like how much am I going to gain if I buy a certain stock. But in real life, it's not that obvious what's regression and what's classification. This is my personal experience. I used to work at YouTube in the recommendations team. And our goal was to show the people the best possible, the videos they want to watch the most. So here's a question for you. Is that regression or classification?
Regression.
I hear regression. Do I hear classification? Seems like classification. So why would it be classification?
Does she like this, or yes or no?
Exactly. It's a yes or no question, right? Like, does the person likely to watch the video or not? And then the oracle tells you, yes, they will watch the video, or no, they won't watch it. And so you go for that. So it is classification, mostly.
It's ranking.
Yes, there is ranking. That would be more ranking. But here's a problem. Here's a problem that we had. How do you tell if the video is garbage? There's many videos that are maybe like an explicit thumbnail or clickbait, or the worst, what I hate with passion is when you see, for example, a sports video and you click, oh my god, I'm gonna finally see the game, and it's a still of the game, and then it turns out that it's just a picture of the game and some idiot talking in the background. But you clicked on that, so you're likely to click. So the algorithm will be like, person's gonna click on this. How do you tell?
Session duration.
There you go. As you probably were going to suggest, regression, right? And session duration is exactly what we're going for. That's how you. Because if you have a video that is garbage, you click on it, you feel bad about yourself and leave very quickly, right? And so what you want is also like this. We'll watch for 2 minutes. That's what you want the oracle to tell you. So it is regression, right? Problem. There are videos that are like 20 hours of a nursery rhyme, and what a better treat for a parent to take that video, put it with the baby to sleep, and go have some sleep and let the video running for the entire night. Those videos get a lot of watch time, but you don't want to get a bunch of like those recommended. So at the end of the day, it's a combination of classification and regression, and in real life it's like that. It's going to be a combination of many more things. There's never going to be like, oh, we did this algorithm for this and it just worked and we go home. No. So what combination of classification and regression? They're still figuring out. We were still figuring it out when we were there, and I think they're still at it. They do very well most of the times. Sometimes not so well. See, I was watching Moonlight Sonata, and I get recommended this video called Wrong Leg Disney Princess Frozen Moana, Princess Anna. And I knew that it was somebody messed up the regression and classification things, and so I sent my friends of YouTube from my team a message saying, whatever party you're having at YouTube, I want in, but please somebody get back and fix this. So anyway, this is a picture of machine learning, but now I have like a more meta question, and the question is, do we understand machine learning? And this is a crowd of experts, so I'm wondering, what do you guys think? Do you think we understand machine learning, or do you think we're somewhere there? Or no. I see a lot of nodding. I actually think I don't really. I don't think we understand some stuff about it. Yes.
What do you mean by that question? Do we
exactly?
understand?
That's a question. What do I mean by that? I don't know what I mean by that, but I'll elaborate a bit of what I mean by that. So let me actually take our example for this talk today will be neural networks, okay? It's kind of like the trendy, sort of ubiquitous object in in deep learning. So let's actually think, what do you think? How many people here know neural networks? Or know what they are familiarized? Cool. Some people do, some people don't. Great, this is perfect, because it's for both. What is the first mental image you had when you thought neural networks? A brain, some kind of like association, something a little sci-fi. When I first heard about it, a friend was like, oh, they think like the brain, and I was like, wow, so this is kind of like what I thought when I first some kind of robot, some kind of like brains connected in liquid and some machines or something. That's kind of what I thought when I heard neural networks. Or maybe even worse, maybe even something more sci-fi like this.
Yeah.
Right? That's kind of my mental image. But then I learned about them a little more, and I studied them, and I realized they're actually a lot scarier than that. This is what they are. And there's numbers, there's stuff, I don't know. So I didn't really understand them, and so I talked to a colleague of mine, and to protect his identity, I'm going to call him Bob. And so I talked to Bob, and he was a perfect, an expert. He was on a PhD in deep learning, so I went to him and I said, hey, I'm a little embarrassed. I don't really understand neural networks. I was wondering if you could help me out. Maybe you could help me understand them. Maybe. And he was very nice. He sat with me and he said, okay, yeah, let's go over it. And so he drew some picture like this, and he said, oh yeah, there are some variables that are the input. You take this through, multiply it by some weights, and then take the sum, and this is an activation function. Take a few layers, go like that. Get some values, find an error function, and then do backpropagation, which is a derivative. Blah, 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 blah. And in my head, I mean, I think we sat there for a long time, and I, at the end, I think it was finally very clear to me that he also had no idea what neural networks are. Because I imagine, this is the mental picture I had. I had a little daughter, and I imagined his daughter asking him, hey dad, I got a birthday party in half an hour, and I'm wondering if you can teach me the happy birthday song. And I just picture him going, of course, honey. For the happy birthday song, what you have to do is you have to draw 5 parallel lines. That's going to be your frame of reference. Then you draw this treble clef here, and the point of the song is to actually put some black and white dots, and the black and white dots will tell you some fundamental frequencies, blah, blah, blah. That's what I pictured. Instead of singing the song, right? So I'm picturing his daughter going, come on, dad, sing the song. And when he was explaining this to me, I was thinking, where's the song? Like, sing the song to me. There's a song of neural networks. Please, sing the song to me. And so that takes me to the question again. Do we understand machine learning? I'm going to repeat your question. Do we understand understanding? Because clearly Bob and I had a different idea of what understanding is, right? So maybe let's say this. Is there a consensus on understanding? What do you think? You think a lot of nodding heads? I'm pretty sure there's no consensus on understanding. We all have different versions of understanding. And let's look at a simple example. A bicycle. Do we understand a bicycle? Do you think we understand a bicycle? So there's many ways to understand a bicycle, right? This is the way Bob understands a bicycle. He'll probably just teach his daughter, hey, okay, honey, what do you have to do? You have to create a pedal, and the pedal takes a little chain, and the chain creates friction with the floor, and that's why you go. Some people understand like that, right? Some people understand that it's like, if I can ride a bike, I understand a bike, right? So this would be like the how, right? The application. The how does a bike work? And I think we all get that. I think given enough time and objects and stuff, we may be able to even build a small bike. I wouldn't let anyone ride mine because it would be dangerous, but we could, right? We can describe to someone. But to me, it's a deeper understanding about bikes. I mean, for example, to me, the question that I don't fully understand is, why does the bike not fall to the sides when we're going fast towards the front? Right? That's, how many people, who knows that answer? It's not, kind of, right? It's not an easy question. Physicists, actually, I asked them a lot, and they're like, I'm not sure, it's not the gyroscopic effect, it's not physics. Because if it was physics, you could lock the handlebar and just let it go, and it would go. So the best explanation I've had so far, one of the best explanations I've had so far that kind of makes me happy, is that when you are driving, you're kind of constantly fixing your position. So if you're going fast, you do this, and the bicycle catches a bunch of ground, whereas if you're standing still, you do this, and the bicycle does not. So that's kind of an okay explanation. I think I'm still wondering, but that's sort of the why, right? So there's the how and the why, and maybe understanding is somewhere there. So for machine learning, what do we have? We have the why, which is the mathematical theory behind machine learning, right? All the formulas, all the activation functions, all the algorithms. And then there's the how. And the how is basically making it work. Coding it, building a self-driving car, building a recommendation engine. And I feel like some people understand it, like to understand the why, and some people like to understand the how. Do we have any why people here? Who likes the why? Cool. Who's a how person? Cool, cool. So I'm kind of with both. I started my career, so I was a research mathematician, so I was always a why person. I did not care about applications. Yes, question?
But isn't there an even more broader why, such as why should that theory give you the outcome that you get?
Exactly.
Far more.
Exactly. There's even more.
I don't know if
I think
deep learners have actually an answer to that.
I don't think so. Yeah, and I think, as I said, understanding is very different. So you can add another 10 slides to this, and people can. This is just my point of view, but I'm sure everybody has different understandings, right? Definitely. So I started as a mathematician, so I was always about the why. I was like theory. As a matter of fact, I was like, when they asked me about applications, I'd be like, my work doesn't have applications. It has as many applications as Beethoven's Fifth Theory, Beethoven's Fifth Symphony. Then I changed my point of view, and I went to work at Google. So I was more about the how. So I was a software engineer, so I was more about, does it work? How can I make it happen? And then I decided that neither one of those make me really happy. I feel like I needed a little more. So I said, what's the combination of the why and the how? What do you think is the combination of the why and the how?
Wow.
Somebody got it. Who said the wow? The wow. The wow is the combination of the what and the how. And that's how I understand things with the wow. To me, if the why is like a proof and how is the use, the wow is to me that aha moment that you have sometimes when you understand something. Like, oh my god, I got it, right? Which one of this is better? Well, I think they're two sides of the same stick, and it's really the stick that matters, right? Obviously, I'm biased, and I drew an enlightenment here and code in a board here, so I'm biased towards this one. But doesn't mean it's better. Like when I was in math, many times I understood something that it wasn't true because I didn't have a proof, or sometimes I understood something that could not be implemented in no way. So the three are very important. And now that I teach machine learning and I actually manage a team of educators, I notice that everybody, most people like to understand this in certain ways, and I think it's the richness of combining the three that really teaches. So in machine learning we have that, right? In neural networks we have the why, which is this. We have the how, which is applications, and I'm wondering what the wow is. So today I want to share with you what the wow is for me with neural networks. What is it that when I got a little bit of an aha moment, I want to share that with you. So back to how neural networks look. Neural networks look like this. But after seeing them for long enough and asking people and drawing formulas, coding things, I stopped looking at them like this. I do not look at a network like this. When I look at a neural network, I look at them like this. Okay? So there's a kid playing in the sand, and there are some slightly photoshopped looking red shells and some blue shells, and I tell the kid, hey, can you draw a line that separates those shells? And the kid draws a line, and that's a neural network. That's the simplest neural network, okay? Because at the end, what you want to do is split your data, right? So classification, yes or no, right? So I have my data, form of red and blue points. For example, the red could be sick patients and the blue could be healthy patients, or the red could be spam emails and the blue could be non-spam emails. And at the end of the day, what I want is a model, and what my model does is it draws a line in between, a line or something else, but it separates it. And then if a new email comes in, if it's here, you say, oh, that's spam. And if it's here, you say, oh, it's not spam. You may not be correct, but you're likely to be correct. And that's really what classification is all about. So let me go with an example. Any questions so far? Okay. So let's go with an example. An example is we have an admissions office in a university, and we want to automatize everything. And so we start with, we have an exam. We have two pieces of information. We have an exam and grades, and we want to decide if we accept students or if we reject them. So with our two pieces of data, we're going to create a rule to accept them or reject them. So the rule is going to be as follows. We're going to first look at some data. We have student 1. Student 1 got, let me normalize the scores to 10. So 9 out of 10 in the exam, and 8 out of 10 in the grades. Okay, and that student passed. We accepted them. Then we have another student, 2, which on the exam got 3, and in the grades got 4, and that student got rejected. And then we have a incognito student, which in the exam got 7 and the grades got 6, and the question is, should we accept them or not? What do you think? Should we accept them or not? Maybe, maybe not. What's the model, right? We have to create a model. So what could be a rule that we can use? What do you guys think? If we have 2 pieces of information, exam and grades.
Average.
Maybe the average, right? So the average could be, let's say the sum, same thing. If I add them and I get more than 10, if the average is more than 5, then I accept them. That could be one, right? Any other? Somebody raise their hand. Minimum?
Absolute. Minimum.
Maybe minimum. That's the one after. So you get the one after. Yes. Oh, what about this? What if we say, the grades matter a little more because the exam is like one time where the grades are all over your life. So maybe weight the grades a little more. So maybe let's do like exam plus 2 times grades and say if we got more than 18, then they pass, and if not, they don't. That could work, right? Any model, like 5 times grades plus 17 times the score, times the exam, bigger than 54, they pass. And or we can do, like you said, the minimum, right? We can do something like, okay, what about this one? If the score is bigger than 5 and the grades are bigger than 5, then it has them. So all these are valid models, and all these are neural networks. This is a neural network of one layer, and this is a deep neural network of 2 layers. That we'll see later. But let's focus on the simple ones. Let's focus on the 1-layer neural networks. Okay. So let me look at this in a graphical way. So we're going to put the students in a grid where here's the exam and here's the grades. So the student who got 3 in the exam, 4 in the grades is here, and the other one is at 9, 8. And now our models are lines. So the line that says your average is bigger than 5 is this line. Okay? This is the line that says anything on the top passes and anything underneath fails, because that's the one that, everything on the top has a sum bigger than 10 and on the bottom the sum less than 10. So it could be that line. If it's this line, it's actually this one. Okay? The exam plus 2 times grades equals 18. So those 2 are valid models. Which one do we pick? Who votes for model 1? Let's see. Who votes for model 2? 2 is winning. At the end, what really answers your question is the data. So you look at previous data, and what does the data say? Well, we look at years behind and what decisions we're taking, and that's how the data looks. The blue points are the accepted, the red are the rejected, and it just so happens that this was the line that worked the best. So then, we pick this model, and that's machine learning, and that's basically a neural network. Okay? So how do we pick the model? From all the possible models, the one that fit the data better. Quiz. Does the student pass based on our model?
Yes.
Yes. Good job. The answer is yes, because we put the student over here at 7.6, and it turns out that our student is on the positive part of on the passing side. Notice that it's not perfect, right? Like we missed a couple of points here that are red or blue on the wrong side. That doesn't matter. We're trying to find the best possible line. It's not supposed to get all the points correctly. So what happens? Let's see. What happens if we have more information than exam and grades? What if I have something else like rank? I don't know what rank means, but maybe some rank, school ranking or something.
Or future success.
Sorry?
So you've seen other students succeed and how their careers go, and you look at what they did at that test.
Yeah. Let's say something else, but yeah, even simpler than that. Like if I have another piece of information, right? Then what happens with my model? So now my model doesn't have 2 columns; it has 3 columns. So if I have 3 columns, then now I don't live in the plane, but I live in space. So I live in 3-dimensional space. This line is supposed to come out of them, and now my points just float in space. And now instead of a line, I just have a plane. But it's the same thing. And if you have 1,000 columns, then you just live in a 1,000-dimensional space, and you have a 999-dimensional hyperplane dividing that. You cannot imagine it, but the computer can, because it's just a bunch of numbers and a bunch of columns, and so that's why it's good to do this like this. But now the question is, how do we find this line? I mean, we can eyeball it, but if it's 1,000 dimensions, we cannot eyeball it. So we have to teach the computer how to find the perfect line. Okay? So let me show you very quickly what the perceptron algorithm is, also called logistic regression. They are taught differently, but actually to me are the same thing with a minor difference. What the computer does for pretty much anything is to find the best line. It starts with some random line, and then it goes, "How am I doing?" And then you tell it, "Not so good," or "Yeah, good," or maybe you can do a little better. That's the idea. That's the idea of machine learning. You take tiny steps to get better until you get better. So the computer starts like that with a line, decides that this is blue and decides that this is red, and says, "How am I doing?" So you actually can ask. It asks how it's doing, and then it moves the line around a bit to see how it gets better. So let's actually not just ask us, but let's ask every point, "How am I doing?" Okay. This model is going to ask every point. So we have 4 points. 2 red, these 2 red are in the right place, these 2 blue are in the right place, and these are wrong. So what would the points tell the model?
4 out of 6.
Huh?
4 out of 6 right.
4 out of 6 is pretty good. Yeah, that would be like an error function, you know. Let's go even simpler. The 4 that are good, they say, "I'm good." And now we want to know what is the best thing that these 2 points can tell the model to get better. So what do you think they can tell them?
On the wrong side.
You're on the wrong side, is good. You said?
Move the line, adjust the.
Perfect.
the
Yes,
angle of
move,
the line.
move a little. Move a little. The point is going to tell the line to move a little. So a quiz. Will the point, the specified point, what would it tell the line to move? Closer or farther? Closer, right? Closer. Because if you get closer, a little bit closer, everything is tiny steps, then it just goes a little closer. And then if it tells it again, and it tells it 500 times, one day it's going to be on the correct side, and then it's going to be like, "I'm good." So that's the idea. What we're going to do is we're going to ask, these points say "I'm good," and these ones say "come closer." And so we listen to them. We can listen to them all at the same time. We can listen to one at a time. We can take 5 and listen to them, then another 5. That would be in batch or individually, or there's many ways. To make things fast, you actually pick a few and listen to them a few at a time. But you do this many, many times. So let's say we listen to this one, and we go "come closer," and now we're listening to the other one. This one says "I'm good," and then we go "come closer," and then they're all good. Okay, that's the idea. How many have you seen gradient descent? Have people seen gradient descent? Put up your hand. This really is gradient descent. In gradient descent, you're minimizing an error function by taking the derivative. If you take the derivative and split it through all the points, what really is happening is the point is adding a little bit to the parameters of the line to make the line go a little closer. Okay? What's adding? It's actually adding the coordinates of the points. Think about it to the parameters of the line. So you can see gradient descent like this. It's like steps to get a little closer to the perfect solution, and eventually we hope it'll get to the best solution. Okay. Any questions so far? Cool. So life is not that perfect, unfortunately, because data, unfortunately, is not always linear. What is the potential problem with this model? And let's go as simple as possible. Don't think of anything complicated. What is bad about this model? Does the data look fake? Why does it look fake? Ish.
Too perfect.
It's too perfect, yes. Too perfect, it should not be divisible by line, first of all. There's gonna be this one who wrote a great essay, there's gonna be this one who, I don't know, terrible in some way, anyway. That they didn't pass, so it's not that pretty, but even worse, like...
It's perfectly on each side.
Sorry?
So there's no dot cut in half. Like they're perfectly divided on each side.
There's that too, yeah, there's no dot in the middle. It's a little too pretty. Check this out, look at this student. Got 10 in the exam and 0 on their grades throughout school. Does that student pass? Well, based on our model, it does. Would you trust that student? Seems like they probably cheated on the exam, or maybe we're lucky that day. I don't know, it's kind of weird, right? So, data probably doesn't look like this. The data probably looks like these points maybe didn't get accepted. So, let's say we want a minimum on each, like the model that you suggested before, right? The model that says minimum of this is 5, minimum of this is 5, or maybe even, yeah, maybe something like this, like a combination of two things. So what, we can't use a line anymore. What can we use? A curve could work, right? There you go, that's a curve. That's a neural network of 2 layers. What about 2 lines? That works too, right? You know, you have to be bigger than this line, and you have to be bigger than that line. The 2 are the same thing. 2 neural networks with a different activation function, if that's familiar to you. So something, you know, this kind of model, this kind of thing where you have to make 2 decisions. That's more layers in the neural network.
Why not just use 2 rules? If grades greater than 5, then...
Yeah, that's a good rule, right? This one, but that can be seen as a neural network. But yeah, this are actually we can even go like slightly tilted lines, and that still works, right? But yeah, 2 rules is 2 lines, definitely. So the idea is that these two rules given by these 2 lines just kind of separate, and now instead of having one person making okay, I'll speak faster. And instead of having one person making the decision, then we have 2. We have the judge 1, who says I'm going to put a lot more weight on, say, the exam, and judge 2 says I'm going to put a lot more weight on the grades. And now what we do is, for example, this is the formula for the first one, and this is the formula for the second one, and they get combined. And how do they combine them? Well, we have a president, and what the president does is she looks at the 2 judges, and she says, okay, if they both admit the student, then I admit, and if not, then I reject. So what really happens is, I'm going to draw you a neural network. We have the exam and the grades, and judge 1 does this. That's the model, a linear model for judge 1. There's a linear model for judge 2, and then the president, she just combines these 2 models and decides based on to do. Okay, so now we can have curves. We can have, and that's a neural network. Okay, and so this is how I picture neural networks, and that's just nicer than the picture that Bob drew at the beginning of the talk. So if you want to have a mental image after today, let this be the mental image. This was a little bit of the aha moment I had. Why did I tell you? I told you 2 lines, but there was also like the curve, right? How do we make the curve? So let me be brief on how to get the curve instead of the 2 lines. It's a different activation function. I didn't tell you what activation function. In case you know what an activation function is, think about it. We normalize the score by saying I accept everything on the blue area or reject everything, but we can actually make it a little more smooth. We can give it a score of 0.5 if you're in the line, and then just bigger numbers all the way to 1, and all the way to 0 if you're farther from the line. You never really get to 1, and you never really get to 0, but as you go, it's like 0.999, you know, and the same thing with 0. But notice that this is not a linear function. They're not equally spaced, so it breaks the linearity, if you want to think about it that way. And that's how you get the curve. The president just takes the score from one judge and the score from the other judge in some linear combination, and makes a model out of the results she got from the judges. And that's the idea. So this is the mental picture I have now. Very similar as before, but you take your 2 models and combine them, and in some smooth way you get this nice curve. Okay? So then basically this is how neural networks look to me. Okay? Still nicer than Bob's image. Right? And you have, since I'm running out of time, let me just be brief about this, but if you have 2 times the score of the first judge plus 3 times the second one, you put the 2 and the 3 there. And if this judge is 1 times his time plus 8 times grades, then you put the 1 and the 8 there, and then you put these weights over here. So every edge has a weight based on the model that each judge picked, and that's where those are the numbers that the weights are associated with the neural network. So so let me tell you a bit about layers, right? So this neural network has the architecture is how many layers it has and how big it is. What happens if we make some layers bigger? What happens if we make the middle layer, for example, larger? What do you think happens?
More lines. More lines.
More lines, right? You have more lines, and you can get more creative in the regions that you bound. You can bound like triangles or anything. As a matter of fact, you can bound every region with just enough of these. So there's if you take a neural network of enough of this, you can actually model anything you want. We don't do it because it's too slow. But what happens if we make what happens if we make the first layer bigger? Well, Now we live in more dimensions. We have more data, and so now we live instead of 2 dimensions, 3, and now we have, instead of lines in the plane, we have planes in space. They form weird regions like that. What happens if I make the output layer bigger?
Volume.
You can get, I can get actually more answers. So, for example, if I want to have a neural network, and this is done a lot with images. If I want something that instead of telling me yes or no, I want dog, cat, bird, I don't have to make a neural network for dog and no dog, and one for cat and no cat, and one for bird and no bird. I can actually use the first one and just make the last layer bigger and answer a lot of questions. But what really captures the strength and the power of neural networks is that you can put a lot of layers in between. So you can have layers like this one, right? You can have linear models, the slightly complicated models, and the super complicated. And you can make them as deep as you want. And neural networks can be very, very deep, in many layers. So yeah, that's basically the mental picture I have. So this is another way to look at it. You just basically have people in a company, and these ones are the judges, and they pass their verdicts to someone higher up, bosses, and this one passes to some VPs, and this one to the CEO, and that one at the end. So this is friendlier than that, right? So when I see a neural network and I get too scared, what I do is I put little faces in all the nodes, and then it's all of a sudden it's a little friendlier. Or even better, I put models. I put linear models in the first row, on the first column. I put more complicated models as we go, and I picture that whatever my neural network does is really just bounding some weird region on the plane, or on the space, or in something. So let me, have a couple minutes for applications, or should I?
Yeah, for questions.
You're good.
I can assign a couple of applications. Let me be really quick. So basically, this is my wow picture. This is my wow. I see neural networks like this, right? So that's my my little enlightenment period moment that I had. I can quickly go through a couple applications. Or do you want me to? Okay, sure. Sorry about that. So self-driving car, for example. What happens to self-driving car? You take your image that the car is seeing and put it in a huge vector. I will tell you more about images. But you go through several layers and it tells you what to do. The real one is like this. It's really long. It's how many layers it's got. But that's how it works. Then the plain Go one is also a neural network. You input the board in some way. It's not just grade and test, but it's a bunch of things. Go through a neural network and it'll tell you what to do. So the way I see neural networks is like a magic hat, right? I put in the information and I get information out. So if I put the student that has exam and grades, then this comes in and the answer comes out. Passed or didn't pass. And so every application can be seen like this. Medical applications that you suggested, you put in the temperature, the symptoms, and everything, and it tells you if the patient is sick or healthy. Stock market, you put in a bunch of values for stock prices, etc., and it'll tell you I should probably buy Google or something. What we did in YouTube, we put in a vector with huge information: the age, the location, a bunch of things. Did you watch the video? Did you watch the Despacito video? Did you watch the Pitbull video? Did you watch this? And then you put it into the neural network, and the neural network says you're probably going to watch the Ricky Martin video. Just an example, it's not my music. And with images, you can do it too, right? You put a picture of a puppy and it says dog, or a picture of a cat. That's a friend of mine, cat. He looks a lot like Garfield. I love him. I try to make a cameo of him every time. So you have Garfield. How does it work with images? Let me be brief about how it works with images. How do you put a 4 into a neural network? You're supposed to put numbers, grades, tests, etc. How do you put a 4? Well, I put a 1 in every pixel of a color and 0 on the white pixels, and then just flatten it, and then throw all those numbers into the neural network. And then it says, that was a 4. Actually works really well with handwritten digits. You can do things like instead of getting numbers out, you can get more things out. You can get an image out. So you can do things like transfer learning, right? You get an image of something in a style, and it draws like a town in Bangkok style. I always try to make the great organizers of a country. So we have the great organizers and a picture of Picasso, and I turn this into the organizers painted by Picasso. I'll send you this picture. And we can even do things like text, for example, sentiment analysis. Let's say we're looking at IMDb reviews, and we're going to check if a review is good or bad. So if it says, what a great movie, we say, yes, happy. And that was terrible, then we say sad. So a neural network can be trained to learn this. How? Well, we have to turn the letters, the words into numbers. So what do? We take all the words from A, aardvark to zygote, I think that's the last one, And we just pick the ones that appear in our sentence. So A, great movie, what? And put ones there and zeros everywhere else, and throw that humongous set of numbers into the neural network hat, and it will return, yes, that was good. Or even things like, you know, hello, how are, and it will guess you. Have you tried that in the phone? You know, just get the next word. You just throw in your vector of the sentence, and it will return a vector with one word highlighted, that's you. It's not too good, you know, like some messages are terrible. Like I send a friend a message, oh, brother Mike and I are going to the airport and I will be there at the same time. I don't have a car, so I can get a ride to the airport on Sunday, and I will be at the same time. I don't have a car, so I can get a ride to the airport on Sunday. I don't know if I just ask everybody for rides on Sunday to the airport. I never do, but. And yeah, well, many things. I'm just gonna say we can do image and text generation. You can throw in an image and actually get a description. And even cooler things like you can, instead of getting a value out, you can get an image out. So generative neural networks, adversarial networks can actually draw these birds. You say, draw me a small bird with a white breast, red hair, blah, blah, blah. And these birds don't exist. They're just drawn by the computer. So let me actually, you can draw cats, draw cartoons, and let me just finish with a small image that this is actually a video. You take the horse, and the zebra doesn't exist. You just take the horse and run it to a pair of neural networks, and it turns into a zebra. Notice that the grass is turned into yellow. Do you know why it's turned into yellow?
Zebras.
Most zebras appear in yellow, so the computer doesn't know how to turn a horse into a zebra. It turns this into that, and that in particular just happens to have yellow background. So, for example, if you make it draw a dumbbell, like it will actually draw a little bit of the hand on the side, because what it's used to see, right? Whatever data you put in comes out. Okay, I'm done. Sorry for going a little over time. If you want to see more of this, I have a YouTube channel where I yap all the time. So if you enjoy my slightly nasal voice, you can hear hours and hours of it. I have videos of all these things. I have a blog where I put some articles like this, so enjoy it. And if you really enjoy it, I actually teach this kind of stuff at Udacity. I try to have a different facial hair for everything. This was rough. After Halloween and around November. But yeah, so this is my data, and thank you very much. I don't know if we have time for questions or how many, or I'm gonna let you guys decide.
Could maybe take a couple of
2-3 questions.
Couple of questions. Yeah, sure. Anybody? Let me take
There's one over there.
Yes.
What's the scariest thought you have about machine learning?
That's good. Well, I mean, like I was saying, I think I'm also a little scared that computers will take over. Although humans, I'm a little scared of humans too right now. So I don't know if they can do a better job than us. Like, but yeah, I mean, I wonder how the computers will take over. But I think we kind of really stop the development. Maybe be ethical about it. Yes.
How big of a problem is overfitting when you use deep neural networks and you have a lot of activation functions?
Yeah.
And then you have like something that's very precise but might be...
It's huge, right? It's huge. Let me give you an example of what overfitting means. Let's see. Where's my model? Here's my model. So I pick a line, and that line is pretty good, right? But what if I had drawn a weird curve with like a very, very complicated neural network that goes around here and wraps around this little point, and then wraps around this little point, and then wraps around this one, and gets everything correct? That'd be a terrible model, right? So I really want the simplest one. I want a line. But neural networks have that problem that if you pick a very complex architecture, you may end up with something really weird that doesn't really model with your data. So the answer is we don't really know how to do it. We try a bunch of things and test with testing data, and then we say we try to do as well as we can with a set of testing data. We don't look like you take some data, you don't look at it, train on the training data, and check, and you cross your fingers that it's all good. But it's more of an art than a science. Yeah.
So based on your exposure to other folks in the industry and where people are kind of at in the discussion, what is the status of understanding machine learning? Consensus or not? Or are people just kind of looking like they know?
It's kind of like where fire was when they invented fire. Like I think, like you go, oh, if if I put it, if I touch it, it hurts, but if I put it underneath a bison leg, and then it's good. Like that's kind of where we're at. Until like centuries later, somebody figured out what fire is, and chemical. But I think we're there. We know how to use it. We know some rules of what happens when you use it and how to optimize it. As for why it works in particular, like advanced, like deep neural network stuff, I don't think people really know, but we just trust it enough.
All right.
Someone's made. Oh,
Yeah. Sorry.
Let's wrap it up.
We'll wrap it up. Move over to the next.
I'll be here so I can chat. More with people. Thank you very much. Wow. Thank you very much. Thank you.
All right. Next, we have a great panel discussing. I should probably plug this in. It's going to be more of a product focus, so practical and aspirational aspects of building international AI technologies to empower people worldwide. Woo! Yeah. Panelists, please come up and take a seat.
Take a glass of water because if you want.
I don't think we need this anymore.